Give it a second here. We're going to let it load before we get started. Alrighty, good morning and happy Friday. Today we're going to be we're going to try to use folding diffusion from Microsoft, which we were looking at yesterday. We're going to try to generate a novel protein, and then we're going to try to visualize it in Nanome, the VR visualizing and general kind of just biochem toolkit that we explored earlier in the week. This is going to be a tricky stream because we're going to be doing the generation on our Linux computer, and then we're going to be going to the Windows computer. So we're going to switch computers midstream. So we'll see how it happens. I have it all set up, but it should be interesting. I am drinking Chemex coffee today, so more water, more hydration, more energy. All right. So first thing we're going to do here is we're going to set up our local Python environment. So we're going to go into our handy dev folder. Let's go ahead and clone this repo here. So we can scroll up top to here. What is code spaces? Your workspaces in the cloud. Interesting. All right, maybe we'll check that out some other time. Let's just copy this, and we're going to git clone that. Okay. Now we're going to go into that folder, and let's go ahead and do first of all history grep pyenv. We want pyenv virtual env, and then pyenv activate. Okay, so pyenv virtual env, and we're going to call this one folding diff. All right. Then we're going to pyenv activate folding diff. All right, now we're in a new Python environment specifically for this project. And we're going to go ahead and pip install -e dot, and maybe hr, I think there's requirements.txt. So let's go ahead and install from that requirements.txt. It's going to go ahead and install Torch. Hopefully we can run this on the CPU, but it might take significantly longer. Pre-trained models. Okay, so it looks like we were able to. Why don't we see pip install is complaining that there's an update. Let's go ahead and install that. Update pip. Yeah. We'll worry about it later. Then let's go ahead is pip install -e. Okay. Now we actually, it's out it's -- upgrade, so let's paste that in there. Alrighty, so now we have our Python environment with folding diff. We can actually go ahead and import it, make sure that the module imports correctly. So if we do Python, let's try to import folding diff. All right, looks like it worked. So I think we managed to get all our dependencies right. Make this a little bit bigger. Cool. So why don't we go open a new window here, make it big again, pyenv activate folding diff, and let's go into our little scratch work folder that we have. Bio. Let's make folding diff.py. And we don't want Vim, we want to open VS Code. So let's go ahead and close some of these windows on VS Code, and then we'll go ahead and open the, what do we call it? Folding diff.py, that's what we called it. Okay, now let's go ahead and start copying some of this. We're going to do from Hugging Face hub import snapshot download. Snapshot download finds all the snapshots of a repo files at the specified version. This is useful. You want all files from a repo because you don't know which ones you will need a priori. Okay. We have a utils.data.data loader. It seems like we don't actually need we can just import data loader directly from that. From folding diff import. Yeah, so VS Code, down here you can see it's still on the ESM protein from our previous stream. So let's switch it to folding diff, which has the folding diff dependency. We're going to be importing modeling, and then from folding diff datasets as dsets. Okay, so first thing we're going to do here load the model. Files will be cached for future calls. So go ahead and create the model. Modeling dot BERT for diffusion from dir, and we're going to snapshot download the folding diff cath for WooKevin here. This is this one right here. Folding diff cath. Okay. So let's just see if these imports work or not. Let's go to our terminal here, and we'll try to run this folding diff.py. Okay, you see it's downloading some stuff. Cool, and it seems like it worked, as in it didn't throw an error. So let's go back to our stuff here. So next thing we need to do is load the data set. Well, do we actually need to load the data set here? Clean, noised, iter next. Okay, well, I don't think we actually need that. Let's go ahead and actually see what happens here. Load data set. Might not need this for inference. So we have clean data and we have noisy data. Clean data, dsets dot cath canonical angles only data set, and this is going to have a padding of 128. So that's the max size that we saw in the paper. And trim strategy is going to be random crop. Trim strategy equals random crop. Okay. Save. Why don't we actually, let's close VS Code and reopen it. Just so we can actually have the, no, it's still not getting folding diff. Sometimes it's really annoying. It doesn't recognize the folding diff module, and then because of that, you don't get the autocomplete. What if we just do import folding diff? Okay, and now folding diff dot pretty sure this is fine, right? Being diff. Okay. Go back to our VS Code. So we're just going to import the whole thing, and then here we can say folding diff dot datasets, and there's going to be something similar for the noisy data here. This is going to be noised angles dataset and clean data. And time steps 1000 beta schedule cosine. Beta schedule. All right, so you take the clean data and you add 1000 time steps of noise, right? This is kind of the diffusion model is learning to uncorrupt the noise or denoise. And that's how you get generative proteins, is you start from nothing and then you ask the network to remove the noise, and it brings something out of that nothingness. So if we make our loader, we'll say data loader of noisy data, batch size, let's say 32, shuffle false, and then x equals iterate. Make an iterator of the loader, and then we want the next version of that, and that'll just give us a single data point. Get a single data point, or inference. All right, and now let's actually, yeah, so from the paper, we did end up, I do remember there being a section where this particular diffusion model actually predicts the noise rather than the mean, and then you remove the noise. So we want to give it the corrupted. Then there's the time t, and then there's the tension mask. Okay, so let's save that, and then let's run it. See if anything happens here. Python folding diff.py. Module folding diff has no attribute modeling. From folding diff import modeling, and then from folding diff import data sets, and then we'll do up here, get rid of this, and then get rid of that. Okay, we got two froms here. Let's close out of that. We'll install auto pep 8 just so we can format this real quick. All right, got a little formatting done. And let's see if this runs. Assertion error. No files found in trend folding data cath DOM PDB. Okay, these weights are stored on Hugging Face at folding diff cath. So do we just not have the model, or we don't have the data sets? To train your own model on the cath dataset, okay, you need to actually download the cath. Well, first of all, does cathdir even have a value in this? Oh. So we can go ahead and we can say echo that. Does it actually mean anything? It does not. So let's not even bother with that. So we're not going to actually go ahead and download. Let's actually see what that script does, the download cath. Control, oh, no, we want to be in VS Code, and then let's try to open dev home trend dash dev dash folding diff dash download cath dot sh. There's a better way to do this. Let's go here to our first window in folding diff, and let's look at the download cath script. It should be somewhere here, maybe in scripts. Scripts from hyper, nope. Maybe in bin. No. Maybe folding diff. No. Interesting. Okay, so there is no download cath file here. But it should be fine. We don't actually want to train the data set. All we want to do is sample the protein backbones. So to sample protein backbones, use the script bin sample.py. Example commands do not use to do this using the pre-trained weights described are as follows. This will run the trained model and generate sequences of varying length. If you wish to load the test dataset and include test chains in the generated plots, use the option test comparison. Note that this requires downloading the cath dataset, see above. Okay, so predict or sample from the protein or sample I think it's generate a protein by sampling from model. Okay, so Python run shell command. I think you can just os dot subprocess dot run. Okay, so let's go ahead and import process. Normally we would just run this in the terminal, but I think if I put it in here, dot run, look at that. It's hard. It's pretty good. Look at GitHub Copilot auto completing this pretty nicely here. So we want. Let's go to our. Let's copy this. So we're going to copy this command here. We're going to paste it here, and we're going to kind of break it down. So sample 10 backbones per length, ranging from 50 to 128, with a batch size of 512. Okay, so I mean, this is probably going to run out of memory just because our GPU is smaller. But let's go ahead and try that. So we can save, we can actually open, we open our Hugging Face esm.py. I think in this we actually had right here. So let's copy paste that. This is a nice little snippet that you can use to get the device. So it's either going to be CUDA 0 or CPU get device. Let's go ahead and comment that out. So let's split this up. We got run Python sample.py. Okay, this is close out of that. What is that? It's trash. 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 Okay. This is really what we want here. So we're going to be running Python. Then we're going to put the path to the sample.py. In our case, this is going to be -dev -folding diff bin sample.py. I'm pretty sure that's it. Then -l, and this is going to be the length, and we're going to go. Yeah, let's just try the 50 to 128. Why don't we actually make that some variables here. Let's do max length. We'll say 128, and then let's do min length, and we'll do 50. And why don't we actually go ahead and give these an actual hard-coded type here, and then we'll do min length and max length. Size of generated protein, number of residues. Okay. Then we have the number of backbones. Okay, so -n num samples, I guess. That's a good name for it. And it's per length. Yep. Go ahead and do number of samples per length. That's going to be an integer. That's going to be 10. And then batch size. Batch size. And then the last one here is going to be device, and then device. Okay. And we're going to have to go ahead and do batch size here. We'll try the 512, but I think this will run out of memory. Sample.py will create the following directory structure in the directory where it is run. Okay. So let's actually go ahead and run it and see what happens. Let's go to our second window here. We're going to run this folding diff.py. Can't open file. No such file or directory. Okay. Let's go here. If we look in the bin, there is a sample. Okay, so I think what's going on here is that Python can't find, doesn't resolve the home directory tilde. So let's actually be explicit here. I think it's home tren. Let's make sure. pwd home tren dev folding diff and then bin. Yep. Okay. So let's go ahead and save that. Run it again. Script to sample from a trained diffusion model. Error. -L expected 2 arguments. Maybe when you do this subprocess.run, you need to have the actually need to do this. Let's see. Unrecognized argument. Device CUDA. Okay, so why don't we also put these in the correct format. Get rid of this leading strings here. Batch size, and then we'll do -- device, and then we'll do F device. So let's see if that solves it. Maybe it was the space. Assertion error. Expected home dev better bio to be empty. So let's open up sample.py, see what's actually in it, see if we can specify the output directory. So cat bin sample.py. This is very difficult to see, so let's open up a VS Code workspace here. We'll open up sample.py. All right, now let's see where they have output dir --o path to output directory. Okay, there's also a seed argument, but we want the output dir argument. Okay. Let's go ahead and output dir, and we'll go ahead and put this in -temp -folding diff, and let's also go ahead and do a seed and put the answer to the universe in that. So let's go to here. Let's make a directory in temp called folding diff. All right, now let's go back to our terminal here and we'll run it. Okay, unrecognized arguments output dir /temp folding diff. I'm pretty sure that's correct, right? I think it might have been -o. Try that. All right, perfect. So actually what we can do while this is running, Control-Shift-T. Our computer is dying a little bit. Is we can NVIDIA watch -n0.1 NVIDIA SMI. We're going to make this a little bit bigger. Okay, so you can see here that this is roughly using half the GPU memory. So we're at 4,000 megabytes out of 8,000. 8 gigs, 4 gigs. But I think we were already using like roughly something like 1 gig just on the monitors. And okay, so there we go. It's doing its work, 6%. We're going to sip on a little bit of coffee while it does that. There's your coffee. This computer is really slow. You can feel it. Like even just clicking on Windows is slow. So there's a lot of CPU activity going on. Actually, we can probably open up a new terminal and see what's going on with the CPU. So Let's bring this one down here. Damn, look at that. I can't even, I can barely drag the screen. There's a 50-50 chance that my entire computer explodes right now. LS CPU. No, I think what we want is top. Oh shit. Damn. That is crazy. Percent CPUs. Yeah, so you can look here, Python, it's really small. I wish I could make this a little bit bigger. See if I can here. But yeah, Python here, the top process is taking up a ton of CPU. So this is kind of an interesting model, right? You have, doesn't take a ton of memory on the GPU, but it does use a bunch of the CPU. Right, because if we remember from the paper, the way that this model works, it folds, or it generates the protein residue by residue, right? So it's actually running model inference a bunch of times, right? Because the model kind of just outputs the next residue given kind of the previous residue, at least the folding part of the model. Okay. So we're still at 370 out of 1,000, so it's still going to take a second. And then we'll be able to see exactly what's going on, exactly what gets generated. I feel like we should have just done less steps. Less steps, smaller batch size. Smaller length. I feel like if we killed this now and reran it with the smaller parameters, we'd actually end quicker. I'm gonna go ahead and take a quick bio break while this continues to run inference. I'll return. And we're back. Looks like this is still running, so maybe we can read some of this output here. So angular definitions, right? So these are the angles that describe the relationship and position, relative position of one residue to the other. FT is angular. This is dimension 6, so it probably has something to do with angles. The weights that it's loading are the epoch 1488. So this is what we read yesterday, how the author was saying that even though they trained up until 10,000 epochs, that the best results, at least from a validation dataset point of view, were coming actually relatively early. So 1488 is the epoch for this checkpoint. Sweeping from 50 to 128 with 10 examples at each length. So there should be 10 proteins for each of the lengths. It's sampling 780 times in batch sizes of 512. And it's starting, so the noise that it's starting from, right, is 512, 128 by 6. So, right, when you actually want to run a diffusion model to actually generate something, you kind of do the opposite. In training, you're taking an actual protein and then adding noise, right, and then learning to remove that noise, either predict the noise or predict the mean, or the image, basically. But when you actually run a diffusion model in inference, you're doing the opposite. You're starting from noise and then asking the model to remove the noise. And the noise that they start from is a noise vector in torch of size 512, which is the batch size, 128, which is the sequence size, and 6, which is the angles. So it's a bunch of 128 chain of nonsense 6 angles. Range tensor, so this is basically, I guess, the range that each individual angle can go from. So this first angle, which I think is the phi, can go from negative 3.13 to 3.13, so close from pi to negative pi to pi, pretty close. And all of them are pretty much like that. I don't know why it's very specific, right? Why is it negative 3.14 and 3.13 and 3.12 and 3.13? This seems kind of specific. Potentially unnecessary. Up here in this in the top kind of printout, we have the different loss functions that are being loaded. So you have smooth L1 radian losses, right? So these are L1 losses in radian space that account for the fact that radian space connects back to itself, right? It's like a torus. Is a one-dimensional torus a right description for that? Or, right, a loop, maybe? There's probably some math term for that. A dimension where there is no, it doesn't go from negative infinity to infinity. It just has like like the end of the one part of the dimension loops back to the earlier part of the dimension. Okay, we're almost done here with the inference, and then we'll be able to check out these proteins, and if they're good, I think we need PDB files for the VR visualization, so that's what we're going to try to get. All right, we're almost there. %. It's over. Oh, what? That was just one step? Nah, I think we're gonna kill it right here. Alright. So we killed it. We can see the CPU was released. Now the top thing on our CPU is OBS Studio, which is what we're using for streaming. And our GPU also released all the memory, so we have it at 1040 megabytes, which is kind of the baseline for this computer. So let's go ahead and see what actually got generated here. So I think we put this in cd-temp-folding diff. What is in here? Model snapshot, plots, training, config. Okay, so this is just the model itself and the checkpoint. If we go to plots, what do we got there? Nothing. Okay, so I think what we saw there was steps. So let's go back. And let's make this significantly smaller. Let's do a batch size of 16, which is 2 orders of magnitude smaller. Number of samples per length, we're going to do 2. Another order of magnitude on that. And then let's do order of magnitude on the minimum and maximum length. Let's try something really small here. Let's try 8 is the minimum length, and then the maximum length we'll say is 32. We're still going to keep everything else the same. But while we're here, let's actually see if we go to the folding diff and top, code dot, see if we control shift F this entire folder for PDB. I want to see how to output PDB files. Into the folder that contains the sampled PDB created and run. Okay, so it should create the .pdb files. We just didn't because we stopped it halfway through. So let's go ahead and close out of this and let's run our stuff. So let's go back here and we'll run it again, and let's put up our expected temp folding diff to be empty. Let's go here, folding diff, remove -rf star, and let's go ahead and rerun this. Okay, let's see how much faster this is now. So it feels faster. But depending on how many we have to do, this still might take forever, so. Yeah, this is still not fast enough. Let's go here. We're going to Control C out of this. Remove everything in folding diff, then come here. We're going to just have one sample per length, and we're going to let's do something medium sized. Let's do 32. Okay, and the batch size we'll do 8. So even smaller. Let's try with that. Attribute error, assertion error, sweep min, sweep max. Okay, so you need those to be. Let's do 32 and then 34. Back here, delete the folder, run that again. See what we get. Okay, now we're cooking. Look how much faster that is. All right, perfect. Writing sampled angles as PDB files to sampled PDB. Okay. So now let's go to our folding diff and look at that. What's inside sampled PDB? Okay, kind of looks like a PDB file, kind of looks like something we could use. So let's go ahead and try to switch now. So I'm going to switch to the Windows computer. First thing I'm going to do is I'm going to use Google Drive. So drop files. So Ubuntu Open File Explorer from terminal. XDG open. Let's go ahead, we'll go to this and we'll say XDG open. XDG open this. Perfect. All right, there we go. There are our PDB files. We're going to go ahead and we're going to drag these into our Google Drive. And I'm not showing that in case some of you guys are super hackers and you can see my Google Drive. So let's close out of that and let's try to switch here. So we're going to try to do a little switcheroo. Testing. All right. Perfect. It looks like we were able to smoothly transition. So we're going to go ahead and we're going to load our PDB files and we are going to try and put them inside the headset somehow. So maybe we can upload apps. We're gonna download our two PDB files. Okay. Okay, so maybe let's go to our here. Let's say how to upload a file to Quest Pro. Connect the 2.0, except if you want your computer. Okay, so we need to do it through the USB. Okay. So let's go ahead and connect the headset with the USB. And then we're going to go ahead. I think we need to accept on the actual headset. Okay, we're going to the files here. Okay. So hide device files, show device files. Drag and drop to install an app on this device. So, can we upload to this? Media devices. How do I upload to Oculus? Okay, so maybe I need to switch this over Wi-Fi and reconnect it. Okay, so now that we're connected, newest list. Maybe close out of this. Quest link. Damn, we just can't even like drag these files in. Maybe open devices and printers. I don't know, guys. I don't know what to do here. Maybe we can go to Nanome, just kind of the Nanome browser or whatever you want to call it. Like maybe there's a way to upload directly through their website. Um, 11 days, Hupo bio, meetings, licenses, organization, Okay, what if we say upload files to Quest not showing in Windows. Enable USB-C. Okay, so in developer mode, USB-C, USB connections need to be enabled. Okay, so let's go ahead and do that. Maybe that's what's going on. Why is our headset? Come on, show me the menu. What's going on here? Alright guys, I think we're gonna have to shut off our headset here. Something's going on. So we shut off our headset. We're gonna restart it. And we're gonna see if we can load. Okay, we're back in it. We're gonna go to the developer settings. Allow USB connection. Then we're gonna plug the device. And we're gonna allow access. All right. So we allowed access via the USB in the developer settings, and now we have our Quest Pro. Boom. All right, picture. Perfect. So why is this cast not working? Okay, we're gonna go ahead and we're gonna put our we're going to put the two PDB files that we generated inside our Quest Pro storage. So there's a couple different folders here: pictures, ringtones, UE4, podcast, Oculus, download. Let's go ahead and put it in pictures. Okay, so we put both of those in there in pictures. Generated 1 and generated 2, or 0. So now we're going to go ahead and put our headset on. And unplug it. Put our headset on and see if we can see those files in Nanome. So we can go ahead and give you guys this view, which I think is better. Okay. So we do need to have that open for the stream to actually show. So let's go ahead, let's open our menu. Let's look at the files. And in media, all right, here we go. Generated 1.pdb, generated 0.pdb. These are the ones that we need. So now we're going to go ahead and open Nanome. Okay, there it is. Let's reset the view. We're gonna have to type the password in here, so let me just real quick turn off the streaming so you guys can't hack into my Nanome account. Alright. So now let's go ahead and make a create a room, public room. Let's do a private room. Start single user private room. Alright, and we're going to try to open no filter. How do we open up a file here? Up. Okay, we want pictures. No, we don't want self. Can we like move forward on this? How come I can't click on that? Apply, use connect, hide atoms, apply quick prep, load all frames. So it's inside a different folder here. Maybe we can, let's connect the headset again and see if we can put it inside that specific folder. So we're going to USB connect the headset. And we're going to try to drag and drop the folders directly into... wait up, we need to hit accept here. Okay, allow. Now we're back on our Windows computer. We're on the Quest Pro. We're going into the Android data. We're going to go inside Nanome Curie. Cache. Nope, we're going to go inside Nanome Files. data. We're going to put it in pictures. This is where we're going to put our PDB files. Okay, so we put our PDB files into Nanome, or at least the folder inside the Oculus that contains Nanome. We're going to unplug our headset from the USB, put our headset back on, see if we can find them. All right, so we're back in our headset. We're going to resume. We're going to pictures. Here we go. Boom. Load 2 files. Okay. Where are our molecules? Oh shit, there they are, guys. Let's unlock these windows. We're going to put these over here. And here we go. These are our proteins. So this is pretty badass. Basically what we've done is we've generated proteins using a Microsoft model that generates protein sequence by sequence. We've exported these proteins via PDB file into Nanome, which is this kind of visualization VR game. And here we go, dude. We're actually holding a protein that we created. This protein does not exist. It's a made-up protein that we generated with the diffusion model, and here we are holding it and manipulating it with our hand. And then here's its little buddy up there. And we can see how these are slightly different. Maybe we can select. I think we want to change the view. Let's see if we can change the view. Okay, so we're going to open up the display menu here. We're going to select this structure. Turn the menu back on. Please select a structure. So let's go into select. Okay, we want ball and stick. No. We want to select the entire chain. Yes. And we want the entire chain to be ball and stick. Okay. So let's put this back over here. Actually, let's put the display menu here, right where this monitor is. Okay. So in this paper, remember, the way that they defined a protein is with these sequences, right? Or these residues. And in these residues, there's 6 angles, right? There's, I forget exactly what the angles are now, to be honest, but basically the rotation and torsional components of this here. So actually, if we open up the browser here, macro entry, content display, web browser. Let's open up our web browser here, bring it a little closer. And we're going to search up folding diffusion. This is the paper that we want here. Going to open that PDF. Hopefully it doesn't crash the headset. Okay. We're here in the paper. There we go. So let's zoom in here. This is the image that we want, right? We have a nitrogen, a carbon, which is known as the alpha carbon, another carbon, and then another nitrogen. So when let's put this here, right? We have, let's select the atoms. So this here is the carbon. Then we have the Ca, which I think is the alpha carbon, and then the nitrogen. So it's like this, right? The nitrogen here and this nitrogen correspond. And this torsion angle here, phi, is the torsion of this atom to this atom, right? And that torsion defines that angle. Then we have the bond angle, which is the angle between this line here and this line here, and that's theta 1. And then we have psi, which is the rotation angle between this alpha carbon here and this other carbon here. Then we have theta 2, which is the angle of this carbon, or these two carbons here forming a line, and then this carbon and this nitrogen here forming another line. That's theta 2. Omega is the torsion between this carbon here and then this nitrogen here, and that's theta 3. And then it repeats, right? So then now the angle between this nitrogen and this alpha carbon here would be the next phi in the sequence. So those 6 angles, the torsion here, the bond angle here, the torsion here, the bond angle here, and the torsion here, all define the connection of these backbone of these atoms here that form a residue, and then you take that residue and you get the structure out of it. So why don't we go ahead and maybe take a pic here, because this is pretty badass. Where's the camera? Here it is. Let's flip it. And let's take a little pic here. Let's get the other little protein in here. Make this a little smaller. Bring this a little closer. There we go. Let's take a pic of that. And we're gonna send it. All right, that's pretty awesome, dude. We're living in the future here. But we are literally generating novel proteins with AI and then visualizing them on a VR headset. Hell, I might even be the first person to do that in the entire of humanity, which is pretty badass to think about. But cool. Thank you for watching streams if you've been watching streams this week. And yeah, see you guys next week.